But how the fig leaf, the dress of our modern Eve, is symbolic of a progressive textile industry, producing many kinds of fabric. Fabric like the gauze lacework of this evening gown. Tough fabrics for the big industrial markets. Fabrics for volume sales to the cutting markets. And fabrics for the great retail markets, where they meet the critical eye of another modern Eve who picks and chooses to get the best quality at the lowest price. To keep her buying is the problem of the millman. His is a problem of high-quality production at lowest possible cost. Today, the textile is attacking this problem with scientific modernization of mill, materials, and machinery. This modernization begins with the production of raw fiber and continues throughout all textile production, in the transportation of materials, of worsted, in the embossing of rayon, in the dozens of production steps that lead to the finished product. This is a report to you, the textile industry, on how textile mills are modernizing. The report deals with the chief trends and processing techniques, illustrated by the latest equipment in America's mills and laboratories. Let's look into them, one at a time, to see what they have to offer each millman in the production of today's textiles. First, the clearly marked trend to modern mill conditioning, putting the mill itself into condition for maximum production at minimum unit cost. Proper mill conditioning means first air conditioning for the control of humidity and temperature and for purification of air in the mill. In installations such as an opening room of a cotton mill, cleaning the air of lint, fumes, and dust will mean improved working conditions. With good air conditioning, combs turn out better tops and cleaner yarn without streaks. The drawing of fibers is smoother and more compact, and a cleaner sliver is delivered. Air conditioning avoids daily spinning losses and reduces the number of ends down. Yarn winding is smoother and there's less chafing. Automatically controlled humidity means more pliable yarn, less static, and more pounds per day. In the weave shed, cleaned air reduces downtime by removing much of the dirt that collects in and around the loom, and off-quality, dark shades and seconds can be eliminated in finished products. But the biggest payoff of all comes because personnel feel better about their work. There's no millroom fever here, and morale is high. Modern mill conditioning also requires a new science, the science of industrial lighting. Engineered light conditioning throughout the mill means bright, pleasant surroundings. It provides an even distribution of light without sharp shadows or disturbing glare. With correct illumination, there's less waste and working conditions are safer. In certain types of very fine work, special illumination makes the spotting of defects quicker. And again, because better seeing means better doing, good light conditioning has a lot to do with employee welfare and contentment. Modern mill conditioning eliminates a lot of the strong arm technique of pushing and shuffling, too. Modern materials handling in the mill means newer mechanized methods. Tiering with electric lift trucks puts to use the upper levels of storage space that formerly were wasted, and it frees extra floor space for greater storage capacity. Modern mill transportation smooths and speeds production flow. The strong arm method is replaced by electrical and mechanical muscle power. Modern materials handling has increased production by speeding up handling of the lap in this mill. An overhead conveyor system carries laps from the picker to the card room, keeping each card supplied with a new lap as soon as the machine is empty. In the die room of another mill, an electrically controlled hoist speeds up the handling of warp beams before dyeing. After dyeing, the beam is raised by the hoist. Then it's conveyed to the drying stand. A new electrically controlled blending line feeder system is one of many up-to-date methods of handling stock. This overhead conveyor and storage system makes continuous processing possible by keeping a number of machines automatically and constantly supplied with fiber stock. An excellent example of mill conditioning through modernized materials handling. And finally, mill conditioning means modern electric power distribution. Highly dependable electric power is generated at the powerhouse and then carried over transmission lines to the mill. Alert millmen are turning to modern unit substations for reliable, low-cost distribution of mill power. The unit substation, shown here in scale model, is a new self-contained package for carrying power to centralized industrial control units for your production equipment. Modern indoor control centers save floor space, maintenance is less, and it's flexible for easy expansion later on. Where low voltage power is supplied, up-to-date switchgear with draw-out circuit breakers and adequate interrupting capacity protects both equipment and personnel, lessens stops in production due to blow-ups. Capacitors, too, will help you to increase the capacity of the lines in your mill. The expert advice of your power supplier may mean real savings through the use of modern power distribution equipment. Thus, mill conditioning includes air conditioning, modern lighting, up-to-date materials handling, and better electric power distribution. 4 basic steps in conditioning your entire mill for lower unit cost production. Power at the point of use is the second big trend in mill modernization. On cards, for example, this means that you can apply electric motors where they will do the most good, right at the machine itself. Compared with the old line shaft drive, individual motor drive is cleaner and more flexible. There is no jungle of belts to maintain. Starting is easier. Speed is more uniform. And of course, working conditions are safe. With individual drive, machines such as these knitters can be arranged to save floor area, and the machines turn out a product that's a lot cleaner. Power at the point of use is also illustrated by this winder. By replacing a single motor with 2 motors, yarn tension became more uniform and winder speed was increased. Result, output went up more than 1/3. Here's a rayon spinning frame powered by individual motors. Each bucket spinner has its own motor. The rotor shaft of the motor is the spindle. Another motor operates the godets and the pumps. Still another operates the traverse motion. The result is efficient machine operation and high production of uniform yarn, even when there's some unbalance in the cake. One promising example of the trend to power at point of use is the 2-for-1 twister shown here in the laboratory of the manufacturer. This twister will apply 2 turns of twist for every, and at the same time will increase spindle speed about 20%. An increase in yarn output of 140% is possible. An individual motor will be used on each spindle. By slowing down the usual 14,000 RPM speed of the motor, we can see the double twist to each single revolution of the motor and the spindle shaft. The speed of all spindles will be electrically synchronized. This tensometer shows how closely tension and twist are automatically controlled within the machine. So the 2-for-1 twister is a modern example of new mechanical design coordinated with the electric motors right where they're needed. Power at the point of use. Higher controlled speeds is another production and processing trend that affects almost all phases of the industry. In spinning, higher controlled speeds are being achieved by a pilot installation of an adjustable speed drive for spinning frames. Although final details of this drive are still in the developmental stage, There is encouraging evidence that spinning frames will be able to turn out more yarn than ever before. With a constant speed motor, yarn tension varies, of course, limiting the speed of spinning. But with the new adjustable speed control, note how tension is constantly kept at its ideal maximum, and the machine always runs at the maximum safe speed for each phase of the spinning operation. With this device, spinning frames already in service can deliver more yarn per day at less cost. Here's a full-fashioned hosiery knitter that illustrates the trend to higher control speeds. An electronic brain automatically regulates more than 100 successive speed changes during the 45-minute knitting cycle, and it controls these speed changes so closely that there's no hunting or overshooting, and no bothersome gallop. At every stage, the fastest safe speed is provided, and the finished product is very, very well made. The product, that is. Another kind of knitting machine, a circular knitter, also is controlled electronically. A push of a button at the start of the shift, and the nylon stocking knitter automatically makes the welt with reinforcing yarns, knits the sheer leg, reinforces the heel with extra yarns, then the foot and the toe. A complete seam-free stocking in 17 minutes. And this goes on all day long, automatically. The operator simply comes around to collect the stockings and replace the yarn packages. A new warper drive is another example of the trend to higher control speeds. This drive will handle yarns of any fiber or filament, no matter how delicate they are, because speed is controlled electronically. Yarn tension is uniform, for yarn speed is kept constant within 0.5% throughout the doff as the beam diameter increases. Yarn breaks are headaches in any man's mill. Constant tension reduces them, so there aren't so many stoppages. Slasher drive can now be accurately controlled through the use of amplidyne generators and a slasher control panel. The day of depending on the old feel and guesswork is long gone. Automatic control of both tension and moisture means that the slasher can supply the weave shed with beams of even density, wound with more uniform, stronger warps, warps with exactly the right moisture content. Here's another example of higher controlled speeds. This fully automatic machine winds the standard 6-inch traverse on cones and tubes at a rate of 900 to 1,000 bobbins an hour, and the machine needs only one operator. The portable warp tying machine does its job in 1/3 of the time required by hand twisting in, and 1/8 of the time required by hand drawing in. It will tie warps for similar patterns but different colors just as easily as it will tie identical patterns. The machine works directly behind the loom, so there's no need for removing, transporting, and resetting your weaving element, and loom downtime is cut. In a few minutes, you're ready for the next loom. In rug weaving, electronic drive on an Axminster loom permits properly controlled speeds. The wides can operate at its highest control speed when in production. Electronic drive means controlled acceleration and deceleration. The result? Better rugs and more of them. The need for higher control speeds brought about the development of this cotton loom that runs 24% faster than the older one it replaced, but turns out 40% more cloth. This jump in production isn't due entirely to the jump in speed. The loom has larger diameter beam heads, it uses a bigger filling package, and you can count on it for long, steady service. This loom is equipped with an individual drive motor. New, completely enclosed loom drive motors are smaller, but they deliver the same amount of power. Motors of this type include this one with a built-in flywheel, shown here with the cover removed. These motors may be equipped with a synthetically insulated cable that prevents shorts, fire, and production delay. A significant development in the trend to higher production speeds is this new weaving machine. It uses individual picks in the filling instead of the usual continuous filling. No bobbin winding here, very little wear on the warp, and you get uniform filling tension. A modern example of higher controlled speeds. Finer quality control is another important trend in today's textile making methods. For better quality sliver, less fly, and an improved product, there's the vacuum card stripper. In this device, there's no brush to touch the clothing. The vacuum stripper has cut direct stripping costs and at the same time boosted output. The modern pin drafter includes even the very shortest fibers as it levels out and reduces the fibers. It will hold the uniformity of this 30s yarn closely to half a count. This finer control of quality can result in a saving of as much as 35% in the final cost of the product. The machine is used here for worsted yarns, but it will also handle synthetics or blends. In knitting, finer quality control requires correct tension as the yarn is fed from the beam. A new electronic beam let-off control for tricot knitters has been developed to regulate warp tension. This control permits tension in both hand operation and running operation. In this application, electricity does its work by feeling, while in the weft straightener, it does its work by seeing. The photoelectric eye just takes a steady look at the cloth going through the tenter. When it sees skew, it sets it true, and it will do this even when the tenter is operating at top speed. By eliminating skew, it cuts down inspection time later on, and it makes possible more accurate cutting and making up. It takes over for the operator's eyes and nerves. And best of all, automatic electric weft straightening adds value to the product. Finer quality control in inspection is also possible by using stroboscopic lights. There's a lot of wear and tear on eyes when trying to inspect speeding cloth. But with stroboscopic lights, the weave appears to stand still, and inspection is easy and accurate. This equipment, used here on a tenter, can be used for finer quality control of printed pattern material and in several other ways. A modern batcher drive, all electrically controlled, keeps tension uniform during beam winding operations. By keeping correct cloth tension, this drive prevents crushing of the inner layers of cloth during the winding, promotes smooth roll ends, safeguards the texture and finish. This new die jig illustrates the trend to finer quality control. Consistent, unvarying die work depends on consistent, unvarying tension in the cloth. In this machine, tension is closely controlled electrically. Then to check dye and fabric colors and check them accurately and scientifically, there's the spectrophotometer. This instrument can detect and record more than 2 million different colors. It measures colors mathematically, and it does the job right the first time. The spectrophotometer enables the mill to produce uniform colors in succeeding batches and repeat orders, so there aren't likely to be complaints from customers. It permits exact matching to international color standards, and the answer is always graphically recorded. Still, another instrument for finer quality control is the electronic tensile tester. By compensating for instrument and cloth characteristics, it gives a smooth test at a constant rate of stress, so it's really accurate. This accuracy is made possible by applying automatic electronic control to the pendulum-type tensile tester. For finer quality control of either fiber or roving, an air orifice system of measurement is proving successful. Here is this instrument in a laboratory. Measuring by air pressure the thickness or thinness of a section of cotton roving. Finer quality control here, as in many other processes, helps the mill produce better textiles. Another trend, the trend to new processing methods, is getting a lot of attention from progressive millmen. For example, there's the new technique of infrared radiant heating. Infrared lamps are already doing a multitude of processing jobs: setting starches, drying rayons, pre-dyeing fabrics, drying impregnations, dehydration in sanforizing, drying thread after slashing, carbonizing wool, drying printed cloth, curing dyes. A different type of heating, dielectric heating, is shown here in a twist setting operation. No kinks allowed in these tire cords. Carefully controlled dielectric heat assures a smooth, uniform twist. This fast, modern method heats clear through from the inside out. Note, too, that no special heating cans are needed. You simply heat through the final wrapping and the package comes out ready for shipment. And this is only one of several practical applications of dielectric heating. Nonwoven fabrics illustrate this trend to new processing methods. For example, this material is made by blending cotton and rayon fibers, then bonding instead of weaving them. Then there's an entirely new and different process of making pile fabrics of great density and with long-wearing qualities. With this method, flock is propelled electrically onto cloth backing that has been coated with adhesive. The fibers hit the backing squarely and stick, forming a thick, durable pile. Plain pile fabric for shoes can be made by this process. So can embroidery material, automobile rugs, and fabrics for other applications. From the trend to new processing methods, let's turn to the final chapter in this report: continuous processing, one of the most important production and processing trends in the textile industry. Range operation, continuous processing with two or more machines operating in tandem as a common length of fabric moves through them without interruption. The basis of efficient range operation is the electrical system of coordinating the relative speeds of individually powered units. The range will accelerate quickly. It will decelerate smoothly and run steadily with just the right fabric tension automatically maintained at each individual unit. The electric drive will provide speeds as fast as processing techniques will allow. A compensating gate is one of the most commonly used control devices for the coordination of range speed and fabric tension. Another type of automatic control uses the photoelectric eye to scan a loop in the fabric, or so-called soft motors can be used where the warp of the fabric is strong enough itself to act as a control belt and thus slow down or speed up the motors for correct tension. This is the principle of electrically coordinated adjustable speed range drive, continuous processing for bleaching, washing, dyeing and soaping, printing and plain finishing. In actual range operation, each length of fabric receives identical treatment, so uniformly higher quality of product is assured. The handling of material between machine units is done away with, and in-between losses are reduced. Continuous processing cuts down power and maintenance costs, and production is increased. More goods from the mills of America. Mills who are following these progressive production trends to tomorrow's textiles. Mill conditioning for maximum overall mill production. Power at the point of use, putting electric motors right where they're needed to increase machine production. Higher controlled speeds to closely coordinate each step in fabric making. Finer quality control to meet the growing demand for better textiles. New processing methods to help solve old problems and create new markets. And continuous processing, the modern textile technique of mass production by range-driven equipment. These are the trends to the future, illustrated by some of the machinery and electrical equipment that will lower the cost and increase the production of textiles. in America and throughout the nations of the world. Textiles Unlimited.